So again, continuing chapter 14, kinetics, I'm going to work through these two problems on differential rate law. So again, I don't care with these types of problems what the stoichiometry is. Our order is going to be determined by the chemical experiments that were done. So again, I have A, B, so here's my concentration of A, here's my concentration of B, here's my rate. So you're going to write a general rate law expression for each one of these. So rate is equal to little k times A to the power of M and B to the power of N. And it doesn't matter who is associated with M, who's associated with N, that does not matter at all. Okay, so I'm going to determine M first. It doesn't really matter which one you determine first. So I have to find where A is changing and B is staying the same. Well, if I look at experiment 1 and 2, this is where A is changing, but B is changing as well. So if you have an instance like that, then maybe you need to look at the other reactant first, and then you could go and backtrack it. So I'll kind of show you how that works. So I'm going to look at B instead. So if I look at experiment 2 and 3 here, A is staying the same, but B is doubling. So I'm going to look at experiment 2 and 3 here, and I see that B is doubling. Okay, A is staying the same. So what is happening to the rate? So again, I have to look at these two numbers and see what they are doing. So if I take 14,460 divided by 3,600, I get approximately 4. So I'm doubling the concentration of B and my rate is going up by a factor of 4. So this must mean that N is equal to 2. It is a second order reaction. So now going back to M, okay? Now that I know what is happening to B, I could look at the first two experiments and also consider what's happening to B here. So realize that experiment 1 and 2, so we're looking at experiment 1 and 2, my B is doubling. Okay, it's going from 0.2 to 0.4, and my A is going from 0.1 to 0.3. So A is going up by a factor of 3, okay? So I know whatever I do to B is going to essentially do what to the rate? Well, it's going to multiply the rate by a factor of 4 due to B. I know that because I discovered it to be a second order reaction. So if I look at my numbers here, the 3,600 and the 300, I could see that if I essentially multiply the 300 by 4, I get 1,200. So how do I get to 3,600 is by taking that rate and multiplying it by a factor of 3. So this is according to A, and this is according to B. So A must be, on its own, a first order reaction, okay? So why I show you is sometimes the data is not going to be playing nice with you, and so you're going to have to find the data that works for you and then go from there. So you will always be finding K with units, okay? So always take experiment 1 just so your numbers agree with my answer keys, by the way. So I have 300 molarity seconds. I should make that B, a big M, that looks like meters per second, is equal to K. My concentration of A is 0.1 to the power of 1, that's molarity, and then this is 0.2 molarity to the power of 2. Again, the math is never the issue. K is equal to about 75,000. But the more important thing is the units, okay? So this is molarity seconds. This is K times molarity to the first, molarity to the squared. So essentially, to get rid of this, I have to bring molarity cubed over to the other side. So the cube takes away one of those, and that becomes a squared. So it's 1 over molarity squared seconds is going to be your unit here for this particular problem. Now, in general, okay, in general, you can use this to find the units of K. It is always 1 over the molarity overall minus 1 times time, whatever the unit of time is. What do I mean by overall? Well, if I go back to this expression here, I have molarity to the first and molarity squared. So what's my mole overall is the adding of those two. So 1 plus 2 equals 3, okay? So if I have an overall of 3, if I take 3 minus 1, that becomes a 2, and that is my unit for this particular, and times seconds, 1 over molarity squared seconds, is going to be how you find the units. Okay, I think it's just as easy just to kind of write out the units and see how they all cancel out, but you can use that according to, in most cases, will always work. All right, so why don't you try this next one, and then I'm going to come back and show you the answer. All right, so again, I looked at experiment 1 and 3 to determine how A affected it because A was doubling and B was staying the same. I saw that when I changed the concentration, I doubled the concentration of A, the rate went up by a factor of 4. So according to A, it has to be a second order reaction. So I put A as M, so M is going to be 2. I look at experiment 1 and 2 where A is staying the same and B is tripling. So then I look at the rate. Again, if you need to write this out and divide it out, go for it, okay? But the rate is tripling. So whatever I did to concentration is what's happening to the rate. That must be a first order reaction. So again, finding your K with units, always use the first example, your first reaction up there, so it agrees with my answer key. So here's my rate is equal to K 0.1 molar squared, 0.1 molar to the first, and I get 0.153 mathematically. And again, the overall is 3 here, so it's 1 over molarity squared seconds.